Just a few remarks. See, if I have a conducting material, say, this is a conductor, say, right? Now, essentially electrically neutral, And a conductor is characterized by what? What characterizes a conductor? Free electrons, right? Sumptuous number of free electrons. I mean, they are essentially valence electrons that render themselves free, right? So there are a large number of free electrons in a conductor. In a conducting piece of material, there would be large number of free electrons. Now, these free electrons are in a state of random motion. These free electrons are in a state of random motion. This is one free electron going this way. This is another free electron going this way. This is another free electron going this way. Free electron going this way. Free electron going this way, and so on and so forth. Yes or no? Free electrons in a state of random motion. Right? Now, if they are in motion, they have kinetic energy. If they are in motion, they have kinetic energy. Right? They have kinetic energy. But what is causing this kinetic energy? What's the cause of this kinetic energy? It's temperature. This kinetic energy is actually thermal energy manifesting itself as kinetic energy, right? This motion is essentially thermal motion. This motion is essentially thermal motion, right? It's based on the temperature of the conductor. It's based on the temperature of the conductor. There is this kinetic energy essentially is thermal motion. Because of the temperature of the conductor. Because of the temperature of the conductor. The velocities that these electrons have, because of thermal motion, the velocities that these electrons have, because of thermal motion, is thermal velocity. These electrons have what is referred to as thermal velocity. And thermal velocities in a typical conducting material at normal temperature, regular temperature, say 27 degrees centigrade to 30 degrees centigrade, roughly, is of the order of 10 to power 4 meters per second. Is of the order of 10 to power 4 meters per second. Essentially, what these electrons are doing here is these free electrons. Their motion, if this is a free electron inside the conducting material, it's moving like this. There is an atom with which it collides. It collides with this atom. It reflects. It encounters another atom. It again reflects. And it follows a zigzag path. Because of multiple collisions, it follows a zigzag path. Every electron will follow a zigzag path. With an average thermal velocity of roughly of the order of 10 to power 4 meters per second. Now, this is one collision, this is the next collision, right? This path between two successive collisions is called a free path. This path between successive collisions is a free path, and an aggregate of these paths An aggregate of these distances is called a mean free path of electrons. This is a path, this is another free path, this is another free path. An aggregate, an average of these free paths is what is called a mean free path. The distance that the electron traverses between successive collisions. The distance that an electron traverses between successive collisions, that's a mean free path. Right? Individual case of collision means there are many collisions, and an aggregate of all collisions put together, we arrive at a number which is the average separation between successive collisions. That's what we refer to as a mean free path. And the interval between two successive collisions. The interval, this is one collision, this is another collision. The interval between two successive collisions is called a relaxation time. Is called a relaxation time. Is a relaxation time. The interval between successive collisions is a relaxation time. There is a mean free path and there is a relaxation time. Right? Now, essentially then, when the only motion that these electrons have is because of temperature, thermal motion, there is a mean free path. And if I take a small piece of conducting matter, which has a large number of electrons, right? Say the thermal velocity of, let's say, one electron is found to be u1. The thermal velocity of another electron is found to be u2. Say this is u1, this is u2, this is u3, this is un. These are the thermal velocities of a set of electrons in a piece of conducting material, in which, let's say, I am evaluating n electrons, large number of free electrons, right? So there is thermal velocity of one electron, there is thermal velocity of another electron, there is thermal velocity of the third electron, and let's say there is thermal velocity of the nth electron. And if I divide this by n, this will give me the average thermal velocity, which will give me the average thermal velocity. Velocity, not speed. Average thermal speed continues to be some 10 to power 4 meters per second. Average thermal speed is 10 to power. This is average thermal velocity. Right? U average thermal velocity. And these directions are random. Direction of u1, direction of u2, direction of u3, direction of u4. They are random directions, right? Directions are truly random, because in a piece of matter, conducting matter, there would be a large number of electrons, right? N would be large. And for every electron that has a direction like this, you would find an electron that has an opposite direction. Because of the randomness, true randomness, if there is an electron in that piece of matter that has a velocity in this direction, then you will always be able to find an electron having velocity in the opposite direction. And essentially then, the vector sum of these velocities would be 0. The vector sum of these velocities would be 0. So the average thermal velocity, not speed, average thermal velocity has to be 0. Average thermal velocity in a piece of matter has to be 0. Average thermal velocity has to be 0 because of the true spirit of randomness. Because of the true spirit of randomness, average thermal velocity has to be 0. Average thermal velocity will show no specific directional bias, will show no specific directional bias. You know what I'm saying? Which means, if in that conducting piece of matter, n of course is a very large number. When you take n very large, it has to be very large. Even in a small piece of matter, n would be very large. There would be sumptuous number of free electrons. And say if this was a piece of conducting material, and I say looked at a certain cross-sectional area. This was a certain cross-sectional area, right? This was a certain cross-section that I looked at. Then, in a given time, the number of electrons that would have crossed from left to right would be equal to the number of electrons that would have crossed from right to left because of the randomness. The number of electrons that would have crossed from left to right would be the same as the number of electrons that would have crossed from right to left because of the randomness. Consequently, across this cross section, there is no perceivable flow of charge. There is no perceivable net flow of charge, right? So across this cross section, what we find is no perceivable net flow of charge. No perceivable net flow of charge across this cross section. This is what we find because of the randomness, right? The whole thing revolves around the average thermal velocity being 0. So in a given time, the total amount of electrons that would have crossed this cross section in this direction will be equal to the number of electrons that would have crossed over in the opposite direction, causing therefore the cross section to behave like no net flow of charge across it. Yes or no? Right now? That means even though the average thermal velocity, magnitude of average thermal velocity, that means average speed being 10 to power 4 meters per second, it's as useless as you could imagine. It's not effective across a given cross section. It does not manifest in any form. Because of the randomness exhibited. It does not manifest itself in any one direction. Right? Now, I change the scenario a little bit. So, one thing you understand, that in a given piece of matter, conducting matter, there are a large number of free electrons, consequence of valence electrons. They are in random motion. Their motion is by virtue of temperature and therefore thermal motion. Their velocities are referred to as thermal velocities. They have velocities in all possible directions, and therefore the net velocity has no direction. Therefore, the net velocity has no direction. The average thermal velocity is 0. The magnitude of the thermal speed on an average typically is of the order of 10 to power 4 meters per second, which is very high, which is so goddamn high, but useless. but useless, right? Now, I changed the scenario a little bit. What I do is, let me look at a mechanism whereby I create a uniform electric field along the conductor. Let me forget what's going to do that, but let's say I've created a mechanism that will create a uniform electric field along the length of the conductor. Uniform electric field along the length of the conductor. There is some mechanism that will create a uniform electric field along the length of the conductor. If a uniform electric field is created, that means if you move along the electric field, there would be drop-off potential. This therefore would be rated higher potential compared to this. If this is rated as higher potential compared to this, then in electrical notation, we refer to this as plus and we refer to this as minus. Positive charges will experience force in the direction of the electric field, but negative charges will experience force opposite to the direction of the electric field. This is what transpires, right? Now, if there is an electron, the charge on an electron is of magnitude E, right? The charge on an electron is of magnitude E. It will experience a force opposite to E. That's the force experienced by an electron in the conducting matter now. Force experienced by the electron is going to be this, right? Opposite to the direction of the electric field. And there would be an acceleration associated with the electron. That's going to be this by m, where m is the mass of the electron. E is the magnitude of the charge on the electron. M is the mass of the electron. Then this would be the acceleration of the electron, right? And all electrons will have the same acceleration. All electrons will have the, I'm talking of free electrons, all free electrons will have the same acceleration. Acceleration of free electrons. Yes, I've created a uniform electric field along the length of the conductor. Because an electron will experience a force opposite to the direction of the electric field, isn't it? Negative charges will experience force opposite to the direction of electric field. Positive charges will experience force in the direction of the electric field. That's why a minus sign. I'm talking of free electrons. So this is the force on the free electron divided by its mass. That's the acceleration of the free electron. Yes or no? Right? Now, look. Say, let me take one of the electrons. And let's say T is the average relaxation period for an electron. T is the average relaxation time for an electron. Right? That's the time in which it undergoes no collision. That's the interval between two successive collisions. Right? The velocity, let's say, of one of the electrons, whose thermal velocity was u1, t seconds later, before its next collision, its velocity is going to be initial velocity u1 plus a into t. Case of constant acceleration, velocity of one of the electrons now the velocities will get changed, right? Because electrons are subject to acceleration. Why acceleration? Because of the electric field, forces of the electron. Velocity of the second electron, u2 plus at2 t. T is the average relaxation time, relaxation period. I'm oversimplifying the model. The idea is to communicate the concept. So in a certain sense, you know, I'm simplifying the model. There are many objectionable areas in what I'm saying, but just to drive home a basic concept, I'm simplifying the model. AT, V1, V2, Vn now are the velocities at the end of t seconds, one relaxation time, average relaxation time for the n electrons. For the n electrons, right? Earlier, if u1 was the velocity of this electron in thermal motion, then until its next collision, its velocity will remain u1. But now, before its next collision, which is t seconds later, its velocity will become v1. Velocity of the second one will become v2. Velocity of the nth electron will become vn. Yes or no? Clear? So these are the revised velocity profile of the n electrons that I am investigating, right? Now let me add all of these. Let me add all of these, right? So if I add all of these, I get v1 plus v2 plus vn equals u1 plus u2 plus un plus a into nt. A into nt, yes or no? T is the average relaxation time. T is the average relaxation time. But u1 plus u2 plus un is 0. Because of the randomness, u1 plus u2 plus un is 0. So this part is 0. This n I can bring down here. This n I can bring down here. So if I do that, then I end up getting, this part is 0. Realize that from these considerations. Then I end up getting v1 plus v2 plus vn by n equals at equals at. T is the average relaxation time. T is the average relaxation time. A is the acceleration produced by, A is the acceleration produced by the electric field on each of the electrons. Then this v1 plus v2 plus vn, these are the velocity profiles after an electric field was, uniform electric field was applied to that piece of matter, conducting matter, right? This v1 plus v2 plus vn by n, now this is called drift velocity. This is called drift velocity. This is called drift velocity. And in general, this t is very, very small. This t is really small. So even if, and this a again is given by this, E by m. And you know, this a again can't be significantly large, even if it is, if you apply very high values of electric field. This t is so small, that actual calculations reveal that this drift velocity will be really, really small. This drift velocity will be really, really small. In fact, we'll do some computations later on, but as of now, let me tell you that this drift velocity roughly would be like having a magnitude of 1 millimeter per second. 1 millimeter per second. Would be roughly 1 millimeter per second. Don't worry about it. A into t will be very small. Okay, because t is very small. t seconds later. Yeah, I mean, these are the velocities resulting after an electric field is applied. This is the average velocity of free electrons after the matter is subject to a uniform electric field, right? So then this then turns out to be the drift velocity, the average drift velocity of the electrons, right? Now, consequently, see, in the original piece of matter, electric field E was applied like this. Before E was applied, say if this was an electron, if this was an electron, it would have come to this point at the end of t seconds. It would have come to this point, right? It would have gone to this point. But now, there is an acceleration in this direction of the electron. There is an acceleration in this direction of the electron, so it doesn't take up this path. This electron takes up some other path, and it drifts this way. It drifts this way to the left. Yes or no? The electrons have a leftward acceleration, so instead of going to this point, it would have got shifted leftwards. It would take up some other path and it would shift leftwards. Let me take an electron that was going this way. It would have come to this point, but now this electron is subject to a leftward acceleration. It would take some other trajectory, and at the end of one relaxation period, it would come here. That means this again would have got shifted leftwards. Yes or no? Look at a third electron. It would have come to this point. Had it not been for the electric field, just by dint of its thermal motion, it would have come to this point. But it has a leftward acceleration. It would now drift this way. Yes or no? Because of a leftward acceleration. So essentially, all electrons seem to now have a bias. They are all drifting leftwards. They are all drifting leftwards. They are all drifting leftwards. And do you realize that the drift velocity is in the direction of acceleration? Isn't it? The drift velocity is synonymous with the direction of acceleration, right? That means every single electron is having a net leftward displacement, having a net leftward displacement. Yes or no? Unlike the previous case, this case where it was random, the net of all displacements was 0. The net of all displacement, but now the net of all displacements is not 0, is leftwards, Now, in this piece of matter, if I had to look at a cross section, in this piece of matter, where I subject it to an electric field, in contrast to the cross section that I looked at earlier, which presented no net of flow of charge across that cross section, this time, if I revisit that cross section, because of a net leftward displacement of electrons, this cross section will report to you a different story. This cross section will tell you that a certain number of electrons have crossed over. In a certain time, a certain number of electrons have crossed over. That's because of the net leftward drift velocity. That's because of the net leftward drift velocity. Do you understand what I'm saying? Roughly on an average, yes. On an average, it's going to be, see, this is what? On an average. Again, I've simplified the model, but on an average, you can take that to be the same. So there is a leftward bias created by a rightward electric field. The electric field was rightwards, and now across a cross section you will witness a net flow of electrons. In a given time you will witness a net flow of electrons through that cross section. Yes or no? Now if across a cross section, a certain number of electrons have been reported to flow to the left, have been reported to be flowing to the left, then that's equivalent. That's equivalent to saying that an equal number of positive charges would have flowed to the right across that cross section, right? If I have like minus 5 microcoulombs flowing in this direction in a given time, that's the same as saying there is 5 microcoulombs flowing in that direction. These two statements are equivalent. Although positive charges are not in general available in conductors for mobility, it's electrons that are party to mobility, but an equivalence is justified. A mathematical equivalence is justified. You know what I'm saying? So if I end up saying that the magnitude of charge that has flowed in a small time dt in this direction is dq, magnitude of charge, that means charge contained by a certain number of electrons that would have made their passage through this in this direction, then I can as well say that an equal magnitude of positive charge, this is the magnitude of negative charge flowing in this direction, that's the same as saying that there is the same magnitude of positive charge that would have flowed in this direction. That's equivalent to saying that there is the same magnitude of positive charge in time dt that would have flowed in that direction across that cross section. Although the truth of the story is it's electrons that are passing of magnitude dq from right to left, that's the same as saying that there is an equal amount of positive charge of magnitude dq flowing to the right through this cross section. Yes or no? In the same time dt, in the same time dt. Now this equivalence of flow of positive charge, this equivalence of flow of positive charge across a cross section, equivalence of flow of positive charge across a cross section measures what we define as a current, We define current through this cross section as the charge flowing per unit time, dq dt, that's the current through this cross section, Right? And despite the drift velocity being so small, of the, like I said, of the order of 1 millimeter per second, it counts. It is not useless. Like the thermal velocity that was useless, which was so humongous in value, 10 to power 4 meters per second. But there was no net flow of charge across a cross section, despite thermal speeds being very large. But drift speed being so small is countable, is making it count. Drift velocity is so small, of the order of 1 millimeter per second, but it counts. Yes or no? Do you all understand this? And it's measured by another entity that we define for ourselves, dq dt, rate of flow of charge across that cross section. So this current is like an equivalent flow of positive charge, which is opposite to the flow of electrons, The direction, if electrons are flowing from right to left in this direction, that's called an electronic current. But the equivalent amount of positive charges flowing in an opposite direction, that's conventional current. And conventional current is opposite to electronic current. So they've built the whole gizmo of electricity around conventional current. Even though the charge carriers are electrons, we look at an equivalent flow of positive charge carriers in the opposite direction, and that we measure as the current, which is my conventional way of looking at current. Clear? Now, if there is a, so after having maintained the ends at a certain potential, creating a uniform electric field along the conductor, creating directional bias for velocities, resulting in a net drift velocity, helping us define a net flow of charge across a cross section, which is current rate of flow of charge, dq dt. Now, if so one thing, if Vd is the drift velocity of electrons like this, then Vd would be the drift velocity of positive charge carriers in the opposite direction, right? So whether I look at flow in terms of electrons or I look at flow in terms of positive charge carriers, I'm going to associate the same drift velocity. I'm going to associate the same drift velocity for both. In the event, I'm measuring current through a cross section. Clear? Now, again, this is a conductor, and I maintain the ends of the conductor at constant potentials. I end up creating a uniform electric field E. From left to right, let's say, from higher to lower potential. And this piece of matter, when an electric field E is applied, results in a current I. Conventional current will be from left to right, whereas electronic current would be from right to left for the figure that I have shown, right? So I'm talking of conventional current now, which is like rate of flow of positive charges through that cross section. Now, if this cross section has an area A, if A is the area of cross section through which this current is flowing, then we define yet another entity for the cross section, which is J, which is current per unit area. Current per unit area is called current density, Current per unit area, and that's referred to as current density. In general, we will look at uniform current I, and J into A will be a constant. If area of cross section varied, essentially what we'll look at, this flow of charge I refer to as a steady state flow of charge. It'll take a little while, maybe a few microseconds or milliseconds for steady state flow to be achieved. If I have a conducting piece of matter with variable cross section, then what we look at is steady state. So if there is current flowing from left to right, a current I flowing from left to right, and this is variable cross section. Now, essentially, whatever charges that enter this cross section are the charges that leave this cross section. Charges are not getting accumulated or held up, just like we had flow in fluids. In this case also, we look at steady state conditions where whatever charges that enter a cross section are the charges that leave a cross section. So whatever current enters a cross section will be the current that leaves that cross section in the same time. So if a current I enters this cross section, there would be a current I associated with this cross section as well. So current will remain the same. So if A is varied, see across this, suppose this is A, then J into A, that will be a constant I under steady state conditions. Current density into area of cross section will be the same current. J is the current density, so if A is varied, J will vary. In this case, when I am going from left to right, I is remaining the same. That's conservation of charge. That's conservation of charge, right? So if A is increasing, J must decrease. If A is increasing, right? In this case, from left to right, area of cross section is increasing, so current density will decrease, so that their product is maintained constant. That product is current, which is about the charges that are flowing through a cross section. And we will assume that steady state conditions are analyzed, where charges that enter a cross section are charges that leave a cross section and enter another cross section. So there is going to be the same dq dt associated with every cross section. There is going to be the same dq dt associated with every cross section. That's a steady state that I'm going to assume. There is another steady state notion. This is steady state in terms of current through various cross section. However, the current through a given cross section could be a function of time. Current through a given cross section would be a function of time, right? So then, at that instant, the current through this cross section will be the same as current through this cross section, will be the same as current through this cross section under steady state conditions. If at a later instant, this current I changes,